Okay, welcome everyone to my continuation of what is algebraic topology. As usual, algebraic topology is a mixture between algebra and topology, right? That's hence the name. And today's topic actually is really at the intersection of algebra or group theory and topology. So I would like to explain what a Cayley complex is. Or in other words, I would like to realize groups geometrically using the structures we have already seen. Cell complexes, and fundamental groups, coverings, and such things. So the starting point are Cayley graphs. Cayley graphs are graphs, and they are very easy to be defined. So you pick your favorite group, and you choose a set of generators for your group. So, for example, Z mod 3. Z can be generated by one element that I call A, and it has one relation, which is A cubed equals 1. And you can form a graph by just, well, the graph has the elements of your group as vertices. So this is the unit, this is A, this is A squared, and you add an edge between them, an oriented edge, if you can go from one element to the other by applying one of your generators. So you should also think of these edges as being colored. I will show you another example in a second. But of course, if I just have one generator, then I don't need any colorings. Anyway, so I draw an edge from 1 to A, because if I multiply 1 by A, I get, well, 2A. I draw an edge from A to A squared, because if I multiply A by A, I get A squared. I draw an edge from A squared to 1, because of this funny relation. This would be A cubed, but A cubed is 1. Cayley graphs are, well, therefore a way to realize groups as, well, as topological spaces, because these are, of course, one-dimensional CW complexes, right? Just the zero cells are just the elements, and I just explained how to construct the two cells, the edges. This whole thing has two flaws. So first of all, the fundamental group is not what you expect it to be. So I would rather like it to be Z mod 3, of course. But if you recall, the fundamental group of graphs is always a free group, and in a certain number of generators, namely by the number of generators given by the complement of a maximal tree. So here, in this case, one generator, so this is Z, which is pretty far away from Z mod 3. So in some sense, this is not the right topological space I would like to associate to a graph, to a group. And yeah, another problem is, so those things, as I just said, is not very good. But another problem is that this really only implicitly, well, I write it does not take R into account. It does, of course, kind of implicitly, because I just said instead of adding a new edge here to A cubed, I know that those two are the same by the relations. But this is kind of sneaky way, or um, not really explicit way of taking R into account. Much better would be to have a topological space where I really can literally read off R. And that's the whole point of defining Cayley complexes. So instead of Cayley graphs, I would like to tell you about Cayley complexes. They use Cayley graphs, of course, but they encoded relations as well in the following way. I'll show you an example in a second. But basically, the relation should correspond to disks that you will glue in. Why? But does it make sense? Well, pi1 is a free group, and every group is a quotient of a free group. So how do we get from from pi1 being a free group to pi1 being a finite group? You add relations in the sense of topology, and well, pi1 is taking loops, right? It's a relation. It's a group defined by loops. So how can you kill loops? So you can impose relation on loops. Well, by gluing in disks. So let's make this precise, or let's make this precise in an example. So I would like to now consider, instead of z, I take z squared. Okay, so my so this is z squared, and of course it looks like a lattice. It's just the lattice z squared in r squared, for example. And this picture, by the way, will be r squared, but I will come to that in a second. So this is z squared and r squared, and I take the obvious presentation of this guy. So I have edges A. There's the blue edges. I should make them blue. Blue edges A, going from west to east. and I have my green edges corresponding to the generator B, and they're going from south to north, right? So if you want, you can choose a point here, you can choose an origin here, and you could, for example, call this point 0, 0, and then, well, this operation is plus 1, 0, and this operation is plus 0, 1, right? Okay, so that's the Cayley graph for z mod z squared. Okay, it still doesn't really see the relation, and the relation here is I walk around a square. So I go A, well, maybe I need more space. So I go A, B, A inverse is going backwards, and B inverse. And what I do now is I go to consider absolutely every vertex. I look at my favorite vertex. This is my vertex. I do it for everyone. And I go this relation, and every time I glue in a disk. Right? For each relation, I glue in a disk. I go with this relation, I glue in a disk. And the relation should be written like something equals 1, because then I'm sure that I'm going a loop. Okay, so here on the right-hand side, I've illustrated this. So for every purple vertex, I glue in a purple disk. For the white vertex, I glue in this white disk here. For the purple one, I glue in the purple one again, and I'm just using colors to distinguish those. For example, for the yellow one, I would draw in this yellow disk here, which you can't see, so I should use black. So this yellow one here, and for the red one, you would include this red one. So for each vertex, you glue in exactly one disk, right? That's good. Take every vertex, take every relation, apply every relation to every vertex, and for each those things, you glue in a disk. You want to kill all possible relations in this new complex. In this case, you just have one disk per vertex, and it's exactly filling in those holes in the grid. And that's why this beast is R2. And I call this the Cayley complex. So this is my R2, the Cayley complex. And I just did exactly that. I got rid of the disks, right? And now I have the obvious Z mod 2 Z cross Z2 action, Z cross Z action on this. Just it's literally built by the translation action of well, this is explained here on the right hand side. And if you take this quotient, now all the disks become trivial, or now all the disks become identified in a certain way. So identifies this point here with all of its orbits, so this point and this point. So every middle point gets now identified, and everything collapses to just one square, which is then the usual realization, one square that looks a little bit like this, which is then the usual realization of the torus. So this quotient space is actually the torus. And observe that something funny happens. So first of all, you get this covering of R2 covering the torus, but you also get that R2 has a trivial pi 1. Okay, yeah, sure, that's pretty obvious. And the pi 1 of my torus is actually the group I started with. So what have I done? I started with a Cayley graph of group. I glued in disks for all of my relations. I had still, because I did this in a well, kind of in the obvious way, in some sense, I obtained the obvious group action on this. I take the quotient by that, and I get a topological space which has the fundamental group I wanted it to be, namely z squared in this case. So let's have a look if this actually works for any group, right? So let's have a look at something finite. Something finite is a bit more complicated, but the cookbook is the same, so the procedure is the same. So you start with the Cayley graph, and the Cayley graph for Z mod 3 in the presentation from before is this one, of course. And now you glue in a disk for all vertices and all relations. Okay, I only had one relation, a cubed equals 1. But I have 3 vertices, 1, 2, 3. And what I did here is for each vertex, I glued in a corresponding disk, and it was the same. So for this vertex, I go the loop and I glue in a disk. Let's say it's the green one. For the other vertex, I go a loop and I glue in a disk. So this would be the whatever purple one. And for the last vertex, I do the same. I go the loop given by the relation, and then gluing the corresponding disk. So the bottom one in this case. So this is a slightly funny, uh, well, topological space that you get. This it's not a manifold anymore. It's like a disk with a mini disk in the middle. So it's like a sphere with a mini disk in the middle. Okay, and you still have, of course, a free Z mod 3 action on this, to basically by permuting everything you see, or whatever, translating everything you see in exactly this fashion here, but also now for the disk itself. And if you take the quotient, you get a topological space which has exactly the same properties again. Uh, this thing upstairs here is a covering with trivial a fundamental group, and the group the topological space downstairs has a good pi one. The space itself is not so easy to imagine, so it's not embeddable into R3, but it works like a little bit like as follows. In case you can imagine it, it's like a Möbius strip that you close, but now with a Z mod 3 symmetry. I will kind of show you the Möbius strip in later on with the Z mod 2 symmetry. Not quite the Möbius strip, you will see. It will be the projective plane, but that's almost the Möbius strip anyway. Anyway, so the difference to the Möbius strip is that I take this symbol, so the letter Y, I let it run around S1. So this is kind of the space that you see here. But you, in order to, well, if you construct a Möbius strip, you twist one of the ends and then glue it together. I do the same here. I twist by a quarter, no, not by a quarter, by a third, and then glue it together again. Of course, a third, not a quarter. To ensure that the boundary of this guy, let's have a look, actually is one closed component. As for the Möbius strip, it goes all the way and then goes in the back, comes back in the front, and turns around here again. So this boundary of this space is actually just one single circle. And into this circle, along this boundary, I glue in another disk. And that's a topological space. And that's pretty hard to imagine. So anyway, so this topological space has the right fundamental group. And it's hard to illustrate, but the cooking recipe is not so hard, right? You start with a Cayley graph, you glue in disks for any relation you see, and take a quotient by the associated group action. And that's then exactly the formal definition. So this depends on my choice of generators and relations, but in a very weak way. But anyway, it depends on this choice, and it works as follows. Take your group given by generators and relations, and you construct this Cayley complex, this tilde one, which is a two-dimensional CW complex, by using as one skeleton the Cayley graph, and then glue in the relations, glue in the two cells along those. So for each G and each relation, you glue in a corresponding two cell, right? For each G and for each relation, I glue in a disk. Right, I have three vertices, I have one relation, so I should glue in three disks. Well, I have infinitely many vertices and one relation, so I should glue in infinitely many times one, and that's what I did. So this is gluing in disks, and you get exactly what you want. So you can take the quotient, and the quotient has the right fundamental group, namely the group you started with. In particular, in this way, you have kind of a topological model of your group, in the sense that pi one of that beast is the group you started with, but it's now a topological space, and you take pi one instead of just having a group, which is pretty cool actually. And you also have the big space, which is the universal cover of well, the one without tilt, and that actually has the action of your group. And that's the one that's the Cayley complex. That's the one that is constructed from the Cayley graph. Okay, I promised you a Möbius strip. You won't see a Möbius strip, you will see a projective plane. Takeaway is, well, that you can construct absolutely any group in this way. Just the spaces might look a little bit strange or funny or interesting, depends a little bit what you want to do. So let me start by doing Z mod 2 for you here live on the slide. So if I have Z mod 2, then the Cayley graph, of course, looks like this. Let's say with one generator, A, And the relation is, of course, a squared equals 1. So I have one relation, I have two vertices, so I should better glue in two disks. And this is done by creating, let's say, an upper hemisphere and a lower hemisphere. And actually what you get here as x twiddle is x twiddle for Z mod 2 is the sphere S2. And the action of Z mod 2 is the antipodal map on this space. So there's the quotient you were looking for, the xg is the projective plane. This is RP2, right? And the projective plane, of course, has the right fundamental group, is Z mod 2, which is not completely obvious, but also not so hard to see. Or you can get it out of by just using what I just told you. By abstract theory, you get that the fundamental group of the projective plane is Z mod 2. Okay, so for Z mod 2, you have, well, basically the classical picture of the covering of S2 given by the antipodal map. So of RP2 given by the antipodal map. If you have a little bit more fancy group, so let's say the direct as a free product of two Z mod 2s, which in generators and relations looks like this. So you have two generators, A and B, and the only relation you have is that each one of them forms a Z mod 2. So it's A squared B squared equals 1. In this case, you have two relations, right? Keep that in mind, two relations. So for each vertex, I need two to glue in two disks. Anyway, so this group is much, it's really not complicated as a group. The elements are just words in A and B. And just whatever. You're never allowed to write AA because AA simplifies. You're not allowed to write BB, but otherwise they're just finite alternating words in A and B. So BAB, BA, B, identity A, AB, ABA, and so on. And this underlying graph that you see here is the Cayley graph. So this is this zigzagging little graph here. And that's pretty clear because all the elements are just alternating words in B and A. And I just write them to the left or to the right, go up to infinity. And now for each vertex, I have to glue in a relation. So let's say I start here at E. So one relation says A squared equals 1. This is a disk I would like to glue in here. So let's say I glue in this hemisphere here. There's another relation that says B squared equals 1. So I glue in a hemisphere here. And you do the same for all other vertices. So each vertex gives you two hemispheres. And in the end, what you get is that x tilde is this infinite kind of chain thing of spheres that are glued together at exactly one point. This infinite kind of infinite necklace of spheres, which is kind of a fun space to think about. And the action, you can actually read off the action of the elements. So A, for example, so AB is an easy element. So AB is the action that shifts everything in this direction, for example, and everything else acts by an antipodal map and a reflection along the sphere. So for example, the element A acts by an antipodal map here and by a reflection along the sphere. So this element AB, right? So you have AB and A acts on this, let's say from the right. So this gives you B, and this is a reflection of this point to here. Okay. So you also have this funny action by an antipodal map on the fixed sphere and a kind of a flip map, an end for end map on the rest, and a translation. So AB translates everything. That's a funny action, and it's maybe not completely obvious, but also not so hard to see that now the space I'm looking for is a free wedge, so the wedge of two RP2s, which is of course impossible to illustrate. It's just or maybe not impossible, but not so easy. It's this necklace of spheres, and now you identify points along the orbit I just explained. And yeah, point is those spaces usually get pretty complicated. They're easy to construct, but they are most of the time very complicated to illustrate. But anyway, so this space has a right fundamental group, which is again not completely obvious. If you would like to, let's say you would need to start by, I would ask you, construct a topological space with this fundamental group doesn't seem to be completely obvious. Anyway, so let me wrap up. So a Cayley graph associated to a group is a very nice combinatorial model of the group. A Cayley complex is even better. It takes the relations into account. It's topological space. And it depends a little bit on the literature, whether you wanted to call it the covering, so the X tilde, or the small one, the X. But anyway, you can construct from it a topological space whose fundamental group is the group you started with. In other words, Cayley complexes give a way to topologically realize any of your groups. And this is pretty beautiful. And this is really at the heart of algebraic topology, right? This is algebra and topology, both at once. Anyway, I hope you enjoyed the video, and I also hope to see you next time.